a design of simply supported one-way slab. Okay, today we will go with the another type of a problem, that is design of continuous one-way slab. Let me share the screen first. Okay, is my presentation visible to everybody?
Yes, ma'am.
Okay. So today we will focus on the design and reinforcement detailing of one-way slabs, which are continuous in nature. So the same problem statement we will consider, which we have seen for yesterday's problem. This was the diagram. In this diagram, you can see that the S1 slab we have designed yesterday as a simply supported one-way slab, and the remaining three slabs, that is S2, S3, and S4, these are to be required these are required to be designed as continuous one-way slab. Okay, so for all these three slabs, the dimensions are same. 4 meter by 9 meter. So Lx is 4 meter, Ly is 9 meter. So Ly by Lx, that ratio is greater than 2. So this is a one-way slab, and the slab will span in a shorter direction, that is along 4 meter. It means along the 4 meter span, we have to provide a main reinforcement, and along the another direction, that is along 9 meter span, we have to provide the distribution steel. Okay, so let us start with the first step, that is finding the trial depth. Now, for continuous slab, if we refer the IS 456, the ratio of L by D, that is span to effective depth ratio, is taken as 26. Okay, so for that ratio, we have to assume the percentage steel, which we have assumed as 0.35, because the steel used is Fe415 or HYST bar. So for that, the range is 0.25 to 0.45. Within that range, we have assumed the value as 0.35. Fs value we have calculated as 0.58 into Fy, which is coming as 240 Newton per mm square. Now for all these data, that is for 0.35% steel and Fs equal to 240, we refer figure 4 given in IS 456, and we calculate the modification factor alpha 1 as 1.4. See, I'm moving very quickly for all these steps because all these steps we have already discussed yesterday in detail. Only the change was L by D ratio, which is not relevant for this alpha 1 calculation. L by D ratio we have to consider in the further formula, that is effective depth D. Okay, so effective depth D is calculated further as span divided by L by D into alpha 1. L by D is 26, span is 4 meter or 4000 mm here, into alpha 1 is 1.4. The value is coming as 109.90 mm. Now again, as discussed yesterday, we have to normally adopt a little higher value for effective depth, so that all the further checks, whatever we consider for the design, that is check for shear, check for development length, for all these, to get all these checks satisfied, we should adopt normally a little higher value for effective depth D. So we are adopting here as 120 mm. Okay. Now as the depth is greater, if you remember yesterday's problem, in yesterday's problem, D was 70 mm effective depth. Okay, here the value is little higher, 120 mm. So as the value is more, we can assume 10 mm diameter bars. And hence the clear cover, again for mild exposure condition, we have adopted as 25 mm. So same value is to be used here. So if our diameter of main bar is 10 mm and clear cover is 25, overall depth D can be calculated as effective depth plus half the diameter of the bar plus clear cover, that is 120 plus 5 mm plus 25 mm, that is coming as 150 mm. So the overall depth D, capital D, for all these three slabs S2, S3 and S4, we are providing 150 mm. Keep in mind always that when you design any continuous slab, the effective depth of all the 3, 4, 5, whatever the number of slabs you are designing as a continuous slab should be same. Okay, effective depth as well as the overall depth should be kept same for all the continuous slab. That becomes easy when we do the construction activity. Otherwise, the centering for this slab, then second slab, third slab will required will be different if we go for different depths. So practically this becomes difficult or complicated. So to avoid that complication and to make the practical implementation easy, we provide the same depth all over the slab for in case of continuous slab. Okay, so now shall we proceed? Is it understood to everybody? First step.
Yes, ma'am.
Yes, ma'am.
So the next step is finding the effective span. Now effective span, I will go to the code now because the criteria for finding the effective span for continuous slab is little different, which we have already discussed last time while designing the continuous beam. But still, I will focus again here the same clause. So everybody open IS 456 page number 35. Is it visible? IS code, everybody?
Yes, ma'am.
Yes, ma'am.
Okay. So for continuous beam or slab, what is the clause? In the case of continuous beam or slab, if the width of the support is less than 1/12 of the clear span, the effective span shall be as in 22.2a, that is as per this clause. That is for simply supported slab. It means if your width of the support, what is the width of the support in our case? What is the value given? Students?
Ma'am, 230
Ma'am,
mm.
230.
230 mm.
230 mm. Okay, so if this effective width of the support is less than 1/12 of the clear span. Now the span of the slab is 4 meter. This is a center to center span, but fine, no problem. We are using that only again. If I will use 4 meter, that is 4000 mm divided by 12, what is the value we are getting? 4000 divided by 12.
333.33.
Okay, so 333 mm is the value. If our width of support is less than this value, it means width of support is 230. It is less than 333 mm. Okay, it means we have to use this clause. That is whatever is applied for simply supported slab. Okay, so the same calculations are done here in the presentation. Is it visible? Presentation?
Yes, ma'am.
Huh.
Yes, ma'am.
So by span by 12, this value is coming as 333.33 mm, which is greater than 230 mm, that is the width of the support. So the criteria for calculation of effective span is like this, which is similar to the simply supported slab. So center to center distance 4000 mm or clear span plus effective depth. Clear span is 4000 minus 230 plus 120 is the effective depth. The value is coming as 3890. So out of these two values, the least value is to be adopted as effective span of the slab. So in our case, the effective span is coming as 3890 mm. Okay. Now the next step is load calculation. So for slab, again, we have to assume 1 meter strip of the slab, that is B equal to 1000 mm. We calculate first the dead load. The procedure is same. Calculate first self weight. So 25B into D, 25 into 1 into D is 150 or 0.15 here. So we will get the value of self weight as 3.75. Simultaneously, please you make the calculation and verify whether whatever the values I have written are correct or not. Okay, so verify this value 3.75. Are you getting or not? The next is
Yes,
flow
ma'am.
finish. Okay, fine. Next is flow finish, which we assume normally as 1 kilonewton per meter square. To convert it into UDL, we have to multiply it by width. So multiplied by 1 meter, we are getting 1 kilonewton per meter. So the total dead load we are getting is 4.75 kilonewton per meter. Now, immediately we are calculating here the ultimate dead load, that is a design dead load, by applying a partial safety factor of 1.5 here. So after that, the design dead load we are getting at 7.125. Okay. Then the next step is to calculate live load, which is given already in the problem, 3 kilonewton per meter square multiplied by the width 1 meter, we are getting it in UDL, that is 3 kilonewton per meter. Again, live load also we are converting into the ultimate live load by applying partial safety factor of 1.5 as 4.5. Now, if you compare this step with the yesterday's problem, there is a slight difference. In yesterday's problem, what we did, we calculated dead load, live load, we added together, and then we applied a partial safety factor, and we have used a single value of the total load for further calculation. Here we are doing the dead load and live load calculation separately, purposely, because there is one important step next, that is finding the moment, bending moment and shear force. For that, we need to calculate these dead load and live load values separately. Why? Let me explain now. Now, we already know that when we analyze any continuous beam or any continuous slab, its analysis is not a simple thing. And it's simply by applying a formula like simply supported beam subjected to UDL, we find out the bending moment quickly by using a formula of WL square by 8. So in the simple way, in this manner, we cannot find out the moments for continuous slabs or continuous beams. For that, we have to make use of elastic methods like moment distribution method or three moment area method or slope deflection method. And based on that, we need to calculate what is the bending moment and shear force at the support as well as at the midspan. Okay. If you remember the design problem for continuous beam, we have already done these steps in the while studying the design of beams. In the same fashion, we have to use now the elastic method to analyze the given slab. This is one method. The second method is, instead of using this elastic method, we can use the empirical method. Now, this empirical method is given on page number 35 of IS 456, clause number 22.5. Okay. So let me open that clause first. Page number 35, clause number 22.5. Okay. This moment and shear coefficients for continuous beams. Is it visible? Code is visible to you?
Yes, ma'am.
Okay. So what is written here? Let me read first. Unless more exact estimates are made for beams of uniform cross section which support substantially uniformly distributed loads over three or more spans which do not differ by more than 15% of the longest, the bending moments and shear forces used in design may be obtained using the coefficients given in table 12 and table 13 respectively. For moments at supports where two unequal spans meet, or in case where the spans are not equally loaded, the average of the two values of the negative moment at the support may be taken for the design. Where coefficients given in table 12 are used for calculation of bending moments, redistribution referred to in 22.7 shall not be permitted. Okay, so this is a very important criteria. This criteria or this particular clause explains us in which situation we can use this empirical method. Okay, what is the situation? That the beams of uniform cross section which support substantially uniformly distributed loads. It means all the three spans. Now here in our case, let us check whether this particular clause is applicable for our current case or not. In our case, there are three slabs or three spans in a continuous slab. All the three slabs are subjected to uniformly distributed load, right? And in every span, whatever the load we have calculated, it is same. There is no variation in the load. Whatever is the span on a slab, so whatever is the load acting on slab S2, the same is acting on S3 and same is acting on S4. And all the three spans of the slabs are subjected to UDL. So our first condition is satisfied. Over three or more spans, either the continuous slab is over three or more spans. Suppose you have only two spans like S2 and S3 only, then this clause is not applicable. In that case, you have to go by elastic method only. Okay, now here in our case, there are three spans because there are three slabs S2, S3 and S4. So this second clause is also satisfied. Which now the spans, value of the spans, which do not differ more than 15% of the longest. Now, what is the span of S2? Span means the value for which we are designing it. Let us assume the center to
4,000.
center distance. Yes,
4,000 mm.
4000 mm or 4 meter. S2 4 meter, S3.
In our case, all are same.
In our case, all the spans are same. So there is no difference between the spans within the three spans of the slabs. Suppose S2 is spanning 3 meter, S3 is spanning 4 meter, and S4 is also spanning 4 meter. So there is a difference between S2 span and S3 S4 span. The longest is 4 meter. So find out the difference between 3 and 4 meter. What is that? In the form of percentage.
One
Percentage.
25%.
25%. So this clause will not be applicable in that case because the difference in the two spans is more than 15% of the longest. Are you getting now the concept clear? So there are three criteria to make use of this empirical method. First is the span must be 3 or more than 3. Second is all the spans are subjected to UDL. And third is the difference between the spans should not be more than 15% of the longest. If all these three criteria are satisfied, we can make use of this empirical method. Otherwise, we have to go for elastic method only, that is by making use of moment distribution method or three moment area or slope deflection, whichever is a suitable method or the method which you feel easy, that you have to use and do the analysis and find out the moments. Okay, is it clear?
Yes, ma'am.
So now this clause, what is the empirical method? The empirical method is given in this table. Refer first now the table 12, which is given on page number 36. Okay, what is given in table 12? It actually gives us the coefficients which can be used to find out the span moments. Now what is the meaning of coefficient? If I will consider a simply supported beam subjected to UDL, my maximum bending moment value is WL square by 8, right? So L by 8 is my coefficient in this case. So in this fashion, all these are the coefficients given in this table. So the values, whatever you are observing, this is not 1 by 12, it is L by 12, L by 16, L by 10. Okay, all these are the coefficients given to find out the moments at appropriate location. Now in case of continuous slab, we have to find out the moment at the span also, that is at the middle of the span, and at the support also over a continuous support. The end supports, obviously the end supports are considered as simply supported, so moment will be 0 there. So at intermediate support, we need to find out the support moments. Okay. Now these moments, span moments and support moments and their corresponding coefficients are given. Now if you consider the coefficient values, two rows you can find out here. In the first row, the coefficients are given for dead load and imposed load of fixed type. Now imposed load means a live load. Okay, the meaning of imposed load is same as that of the live load, but it is a load which is of fixed nature. For example, if we consider a kitchen area of a residential building, and in the kitchen we are constructing the kitchen katta, right? Kitchen katta or kitchen ota, that is of fixed nature. We do not move it every day, right? It is of fixed nature. So it is an imposed load of fixed nature. Or suppose in a living hall you have constructed or you have manufactured and erected one cupboard, which is, or furniture, we have made some furniture which is resting on your slab, which is of fixed nature. We cannot move it. If I want to move it, I have to break it first. Okay, that kind of load comes under imposed load of fixed nature. In other words, a fixed load or a load of a furniture which is fixed, which is not movable, that load comes under this type. So the first value is dead load and imposed load, which is of fixed nature. Second is imposed load not fixed, means a movable load, that means a live load. It may include now the load of a moving person, human beings, or occupants of a particular room, and the other furniture load which can be moved, like a sofa set or a dining table or chairs. Their load is a movable load. Or this type of a furniture is a movable type of a furniture. Its load is considered as a imposed load of not fixed nature. Is it clear? That's why we calculated the dead load and live load separately, and we applied the partial safety factors separately in our problem. Now these are the coefficients. Now how these coefficients are applicable? Suppose we are interested to find out the span moment. Now there are different spans in our given problem. We have three different spans. So first span is the end span, okay, near the middle of the end span. So this is a span moment at the end span. The total load will be L by 12 plus L by 10. Now L by 12, L by 10 only, that is these are the coefficients. Now to obtain the moment, these coefficients are to be multiplied by total design load and effective span. Read the note given below here. For obtaining the bending moment, the coefficient shall be multiplied by the total design load and effective span. So what is the load now, or the moment? If we consider the moment due to dead load near the middle of the end span, the moment will be W into L by 12. So it is WL square by 12. That is the bending moment near middle of the end span due to dead load. There is live load also acting on the slab, so plus WL square by 10. So my total load near the middle of end span will be WL square by 12 plus WL square by 10. Is it clear to everybody?
Yes, ma'am.
Yes, ma'am. Similarly, at the middle of the interior span, these are the coefficients. When we calculate the support moments, at the support next to the end support, these are the coefficients, and at other interior supports, these are the coefficients. So all these I have explained in the form of a diagram, which I will explain here quickly. So these are the tables. The first table, table 12, is related with finding the bending moment coefficient, and table 13, next table is for finding the coefficients for shear. Okay, so this is just one example I have taken to explain you how the formula comes out. So I have considered here example of a 4-span slab. There are 4 spans, S1, S2, S3, S4. So for these spans, we need to calculate the bending moment, total 7 bending moment value. How 7? For S1, the moment at the middle, which is a sagging bending moment. Then at this support, there will be a hogging moment, support moment, M2. Then for second slab, again at the middle, it will be M3. Then at this support, there will be the moment, support moment, M4. Then this is S3 slab, moment will be M5. The next support, the moment will be M6, and finally the S4 slab, the span moment will be M7. So I want to find out all these 7 moments. Now to find out the 7 moments, I have to make use of that table, and I have to write down the expression for getting each bending moment. So this is the S1 slab. Now this S1 slab is middle of the end span. Okay, how I have to consider the criteria here? Near the middle of end span. So this is my end span, and I'm considering middle of the end span. Okay, so M1 formula will be as per this table, WL square by 12 plus WL square by 10. So the expression is WL. Now the first W value is because of dead load, so it is WDU L1 square, corresponding span of that slab we have to consider, divided by 12 plus WLU into L1 square divided by 10. This is the expression for M1. Okay. Now M2 is the moment at the support. Now this support is actually the support next to the end support. This is my end support, and this is the support next to the end support. In the similar fashion, if you consider this another end support on the right hand side, next to this end support, this is the support. So support next to the end support, that is the M6 value and M2 value, both will have same expression. Okay, M2 and M6 both will have same expression. Now what is the coefficient for this support next to end support? So if I will go here, support moment, At the support next to the end support, my coefficients are minus L by 10 and minus L by 9. So this will be WD, sorry, minus WDU into L square by 10 and minus WL uh, WL L square by 9. Okay, the same is written here. M2. See here. Minus WDU into L1 square by 10 minus WLU into L1 square by 9. L by 10, L by 9. These are the coefficients. If you see the expression for M6, it is also the same. Because the condition here is exactly same. That is a support next to the end support. Both these are the supports next to the end support. Is it clear, everybody?
Yes, ma'am.
So we have discussed about M1, M2, similarly M7. If we consider the expression for M7, this is also the end span. So M7 expression is similar to M1. Now coming to the next span, that is the middle of interior span. This particular slab S2 is an interior slab because it is next to the end slab. Here also S3 is an interior slab. So S2, S3, the moment, span moments M3 and M4, their expression will be same. You can see here M3 expression and M4 expressions are same. What is it? It is the middle of interior span. So if I will go here at the middle of interior span, my coefficients are L by 16, L by 12. So the same are applied here. W L square by 12 minus W L L square by 9. This is because of dead load. This is because of light load. Okay. So M3 and M5, both these expressions are same. Now the remaining is the interior support moment M4. Now for interior support, what is the clause here? At other interior supports, the coefficients are minus L by 12 and minus L by 9. So the same are written here M4 minus WD L square by 12 minus WL L square by 9. Okay. Only the thing, what is the important thing? See, for M2, for this support moment, the span we have considered is this L1. Hmm? Similarly, for finding M6, we have considered the end span. For M6, we have considered the end span L4. This you have to check carefully. Similarly, for M4 we have considered the span L2. Span L2. Okay, is it clear? So M1, M2, M3, M4, M5, M6, M7. How these values are calculated, I have explained you through example. This is about the bending moment. Now similarly, we have to find out for shear force. So
Ma'am,
for, yes,
ma'am, we can also take L3 now while
fine.
finding the interior support M4.
Yes, for M4 you can consider L3 also.
Ma'am, if the length is different, then
Though the length is different, finally we have to consider the maximum value of movement for further calculation. So support moment, it will not cause any problem for further design. Okay. And when we calculate the span moment now, for this span moment, we normally calculate the area of steel. And also support moment also we need to consider to find out the additional area. But how to find out that I will explain you. But if these spans are same, then there will be no problem. Suppose L2 is lesser and L3 is more, then the moment obviously it has an effect. This L3 has an effect in this moment M4. And definitely that moment effect will be taken care through the area of the steel required. So in that case, the area of the steel required will be a little bit higher. But anyways, we do not provide the exact steel. We provide little higher steel always. Okay, is it clear?
yes, ma'am.
Now the next is to find out the shear forces. Now let us come to the code again and sorry, instead of going to code, I have included those photos here in this slides itself. So I will go to the slide. So this is table 13. Now in this table, the shear coefficients are given again for dead load. At the end support, the coefficient is 0.4, and for obtaining the shear force, the coefficient shall be multiplied by the total design load. Okay, so total design load is our UDL. So the design load will be W into L. That is the load. So 0.4 W into L will be the shear force at the end support. So in this fashion, this is our end support. The V1, that is a shear force at first support, is 0.4 W into L1 plus 0.45 is because of the live load. Okay. Now, how many are the end supports now? We have this end support and this end support. So expression for V1 and V5 will be same. Now for the interior support, that is the support next to the end support, here at the support next to the end support, two shear force values are given. One is the outer value and another is the inner value. Okay. So outer means at, I will show here, outer means at this side, outer, it means when we move towards the end support, that is considered outer, and when we move toward the interior part of the slab, continuous slab, we consider it as a inner. Okay. Similarly here, fourth support, huh? At fourth support, this is the outer and this is the inner. So at this support, support next to the end support, this 2 number and 4 number, the moment, sorry, the shear force values will be two values. One is inner and outer. Okay, V2I and V2O. What are the values for V2I? I will go back to the this table. For inner side, the coefficients are 0.55 and zero point 0.6 for dead load and live load respectively. And for outer, it is both 0.6. Okay, so the same values are written here. Inner is 0.55 and zero point 0.6, outer 0.6 for both. V2O and V2I. Similarly here, V4O and V4I. These are the expressions. And this is the interior support. For interior support, what is the coefficient? At all other interior supports, the coefficients are 0.5 and 0.6. So for interior support of V3, the coefficients are 0.5 and 0.6. Is it clear, everybody? See here, for finding the outer and inner shear force, the corresponding spans are used. For outer, this span is to be used. For inner, this span is to be used. So for V2I, L2 span is used. For V2O, L1 span is used. Okay. So making use of this empirical method, that is by applying these coefficients directly and getting the shear forces at different supports, is much more easier as compared to application of elastic analysis, because it is a time consuming method, right? If you go for moment distribution method, we have to find out the fixed end moment, then we have to carry out the steps of carryover factor and balancing, etc. We have to find out the stiffness coefficients, factors, then we have to repeat that different steps of balancing and carryover, etc. Then we will come to the end, we will find out the total moment, then we have to draw the diagram again, and we have to analyze each and every span separately to find out the shear forces, and then we calculate the final shear force values and final bending moment values. Okay, that too again, support moment we have to calculate separately based on SFD, and span moments we get only from the moment distribution method. Okay, so that is a lengthy process. This is the shortest way of finding the moment and shear force, provided the given slab is satisfying the given condition in the IS 456. Okay, so for your term work also, when you start designing one-way slab, you have to verify whether the given condition is satisfied or not. That's why I was telling, keep your plan as simple as possible. Otherwise, if you make it complicated, if you put more offsets, if you put variations, large variation in the dimensions of the room, it becomes, the analysis or design part becomes lengthy, not complicated. The process is same. If you identify a given slab as one way, the process will remain same. If you identify it as two way, the process will remain same. But the number of one-way and two-way slabs with different dimensions will be there. Each and every slab you need to design separately. If you have a same dimension, the one design will be sufficient, and the same design will be provided to the another slab also having the same dimension. Load, some or less, it is always same. Okay, live load, there will be a slight variation in the live load. Dead load, it depends upon what sizes you assume for the various structural components. Okay, so practically, even when we, if you visit any construction site, you'll find out a similar type of a formwork being used for the different rooms. So in this fashion, the planning and designing is done so that the practical implementation also becomes easy and on the same side economical. If you go on changing the dimensions in every room for beam and slab, then your formwork required will also will be large. Obviously that will cost money. Okay, because for every room you have to provide the different formwork, then different centering, everything will cost higher and higher money. Is it clear how these moments and shear forces are calculated by making use of empirical method? Now if you are designing a beam, and for a beam also, continuous beam, if your conditions are getting satisfied, you can use empirical method instead of using moment distribution method. Okay, so for your term work in your plan, suppose you are getting a continuous beam and that continuous beam is satisfying the conditions given in IS 456, you can directly make use of this empirical method, these coefficients for designing beam also and slab also. Is it clear to everybody? Empirical method,
Yes, ma'am.
guys.
Yes, ma'am.
Yes, ma'am.
Okay. So we have calculated now the moments and shear forces. This was just an example. Now let us come to our actual problem. So this is our actual problem. We have 3 spans and every span is having a same span, every slab is having same span 3.89 meter. So it is written here. We will have to calculate 5 moments, 3 span moments and 2 support moments. Now, luckily on every span we have a same load, 7.125 is the dead load and 4.5 is the live load. बरोबर आहे ना? डेड लोड किती होता आणि लाइव लोड किती होता?
बरोबर आहे.
हाँ, the first one is dead load ना? Yes, correct.
Yes, ma'am.
15 त्रिक 45 बरोबर. So 3 was the live load ना? So this is dead load and this is live load, and all the 3 slabs are subjected to the same loading. So M1 is actually the middle of the support span, right? I will go back to what is given here. This is the middle of the end span. So for middle of the end span, what are the coefficients? L by 12 and L by 10. So for middle of the end span, that is for M1 and M4, M5, the coefficients are L by 12 and L by 10. So WD is, I have just done one sample calculation so that you will understand how the values are taken. WDU is 7.125 into L1 is the span 3.89 square divided by 12 plus WLU is 4.5 multiplied by the span L1 3.89 square divided by 10. The value is coming as 15.79 kilonewton meter. Okay, so M1 and M5 are same. Similarly, these are the support moments M2 and M4 for which the coefficients are L by 10, minus L by 10 and minus L by 9. The values are put here and the value coming is minus 18.35. M3 is the interior span. For that the value, the coefficient is L by 16 and L by 12. So the values are again written in this expression and the value coming is 12.41. Now we are getting 3 values of moment. Actually, these are the 5 values, M1, M2, M3, M4, M5. But M1, M5 are same and M2, M4 are also same. So out of these 3 values, we have to choose the maximum one for design purpose. Okay. So out of these 3, the maximum is 18.35. So that is our MU max value, that is 18.35 kilonewton meter. Against this MU, we have to check now the moment carrying capacity of the slab. Okay. So the next step, the calculation of shear forces is done. So there are 4 supports, V1, V2, V3, V4. These are the interior supports. So outer, inner, in this fashion we get the 2 values and both the values will be same. See, V2O and V3O both will be same. V2I, V3I both will be same. V1 and V4 both will be same. Okay, by making use of appropriate coefficients, these values are calculated, and out of the three, again we have to adopt the maximum value, which is coming here as 27.13 kilonewton. So our VU is the maximum of 27.13. So in this step, we have calculated the maximum bending moment and maximum shear force acting on a slab. Okay. Now, moment carrying capacity, we calculate the MUR max by making use of this equation. So MUR max is coming as 39.74. This value we have to check against the maximum MU, which is coming as 18. This value 18.35. Okay, so 39.75 is greater than 18.35. So our moment carrying capacity of all the slabs is safe. Okay, now next step is the most important. We are supposed to calculate the main steel. Now, to check the moment carrying capacity, we have compared the MUR max with the maximum moment. But for that maximum moment, we do not calculate the AST. AST we calculate as per the individual span. This is because, see, we already know, I will go back to the maximum MU value. Maximum MU value is coming as 18.35. This is corresponding to M2 and M4. That is for these support moments. Okay, M2 and M4. So whatever is the steel required at the support, the same if we provide at every slab here, our design will be uneconomical, because the every slab is subjected to different moment. See, this slab is the span moment for this slab is 15.79, and if we are calculating it considering 18.35, and if we are calculating the area according to this, we are actually providing more steel here, more than the required one. This is resulting in an uneconomical design. Okay, so to achieve economy in practice, though we consider MUR max comparison with the maximum moment, we calculate the area of steel separately for each slab. Okay, each slab means for each moment, for support moment separately and for span moment separately. Okay, so this is the formula. So now to find out AST1 and AST5, I will go back to the diagram again here. AST1 and AST5, we will provide the area of the steel in this slab and in this slab, because M1 and M5 both are same. Okay, the moment is 15.79. So that value is put here against MU 15.75 or 79, whatever is the value. And for that, the AST value is calculated, which is coming out to be 391.10. Okay, similarly, AST to AST4, it is something 18 point something. For that, the value of area is coming as 460, and AST3 is calculated for M3 value, which is coming as 302.40. Now, all these area of the steel should be compared with the minimum value, which is 0.12% BD, which is coming as 180 mm square. So all these values are greater than 180 mm square. So whatever is the value coming, for that only we have to calculate the spacing further for the bars. So now we have initially assumed 10 mm bar. So for 10 mm bar, the area of the single bar is coming as 78.54. Spacing is calculated again. Now the AST1, AST5 both are same. So we will calculate the spacing for that portion S1 and S5 as 1000 into AST upon AST1, which is coming as 200.8 mm. This is compared with the minimum value 3D or 300 mm. Now this value is lesser than 360 and 300 mm. So this value 200 mm is provided over here. So for slab S1 and S4, now if you refer the diagram again, S2, S3, S4, these three slabs, the slabs we are designing. For S2 and S4, we have calculated now the area of the steel as 10 mm diameter bar at 200 mm center to center at middle of the end spans. Okay. Now for this 200 mm spacing, we are actually calculating what is the provided area, which is coming out as 392 mm square. So very slight difference in whatever is required and whatever is provided. Is it clear, everybody? how we calculate the area of the steel for end spans, that is for slab S2 and S4. Is it clear?
Yes, ma'am.
Then next is calculating for remaining, that is for middle slab, that is for S3. The spacing is calculated by again making use of the same concept. The spacing is coming as 259, or that is approximately 265 will consider. It is compared with the minimum value of 300 mm. It is coming less than that. So instead of 260, the spacing is still reduced and provided as 250 mm. You can even provide no, you have to reduce the value always, not to increase the value. So you can provide 255 also, or 250 mm as a spacing for the bars. So for middle slab, that is for S3, we are providing 10 mm diameter bar at 250 mm center to center at middle or of intermediate spans. Now based on this 250 mm value, again whatever is the provided area of the steel is calculated here. Now, the most important, over the support. Now, I will go back to the original diagram of your problem statement here. See, this is the S2, S3 and S4. We have calculated the area of the steel for this portion and this portion. But there are two supports, intermediate support, where there is a moment acting, because these are the intermediate support of a continuous slab which are subjected to negative moments or hogging moment. For that moment also we need to provide the steel in compression zone. Okay. Now, when you consider any continuous slab, the slabs or any slab, if you consider near the support, we bend the 50% bar and we move the 50% bar in the compression zone near the support. The same thing we have to do for this support. The 50% bar from slab S2 will be bent and provided in the compression zone over this support. Similarly, there is a continuation in the slab. So the reinforcement from S3 slab, 50% of that will be bent and again extended in the compression zone over this support. So if we consider this particular support, the bars are coming from S2 as well as S3. 50% from S2, 50% from S3. Similarly, this support, the next support, the 50% bars are coming from S3 and 50% bars are coming from S4. Now, whatever is the available 50% bars from both the slab, that total area of the steel, whether it is sufficient to resist the movement at this support and this support, that we need to check. If it is sufficient, then whatever the 50% bent up bars are coming in the compression zone, that will be sufficient. If not, then we need to provide the additional reinforcement over those supports. Okay, so that calculation is done further in these steps. Let me explain that also quickly because I want to finish this problem today only. Okay, so over the support, see, 50% from AST1, because that is AST1 is the slab 1, AST3 is for slab 2. Sorry, this is AST1 is for slab 2 and AST3 is for slab 3. I will go back to avoid the confusion. This is the diagram. Okay, this is the diagram. So this is our S2, S3 and S4 slab. So this is actually, here we are providing AST1 and here we are providing AST3 to resist M3. Okay, to resist M1 we have provided AST1, to resist M3 we have provided AST3. So over the support, 50% of AST1 and 50% of AST3 is available due to bent up bars. So AST available over the support is 0.5 of AST1 plus AST2. Now what is the AST1? We have to consider the provided value. AST1 provided is 392 and AST3 provided is 314.16. So 392 plus 314.16, half of that 0.5 I forgot to write down here, half of that is coming as 353.08. So I will quickly make a change over here. So this is 0.5 of total addition. So this is 353.08 mm square. This is the AST available due to bending of bars. Now what is the AST required at that support? The support moment M2 and M4. For that we have already calculated AST2 and AST4, that is 460.4. That is the required area at that support. And how much is available? The available is 353. It means this is not sufficient. How much additional we need to provide? For that we calculate AST2 minus AST available. So 302.40 minus 353. Now this calculation is wrong. This should be AST4. This must be AST4. Wait. Okay, AST2 or AST4. This value must be 402, not 30, 460. 460 point, what is the value? 40. Okay, so 460 minus 353, the additional area required is 107.32. Okay, so 2 more number of bars are required to take care of this area. Okay, so other than 50% bar bent up, we have to provide 2 more number of bars of 10 mm diameter per meter along with bent up bars at both the supports. Is it clear? This is very important, guys, because you're designing a continuous beam. Considering or understanding of this particular aspect is very important. Is it clear to everybody?
मॅम 10 mm चे बार का घेतले आणि दोनच का
10 mm आपण ऑलरेडी अज्युम केलं ना 10 mm बार डायमीटर सगळं आपण प्रत्येक स्लॅब साठी 10 mm बार साठीच कॅल्क्युलेशन केलं ना सो वी हॅव प्रोव्हाइडेड द सेम बार हिअर आपण बेंड करताना 10 mm चे बार बेंड केलेत ना मग नंतर उरलेलं दुसरं कसं काय वापरून चालेल हे डायमीटरचं बार आर यू गेटिंग आणि टोटल एरिया किती आहे 107.32 रिक्वायर्ड आता find out the area of a single bar which we have already done here in the earlier step. What is that value? See here, for a single bar, what is the area of single bar? 78.54. So 78.54 multiplied by 2. किती आली value?
157.07
and किती required आहे? 107. So this is sufficient. Are you getting my point?
येस मॅम
जे बार आपण बेंड केलेले आहेत
ओव्हर रेनफोर्स नाही
हा थोडंसंच आहे ना जास्त नाहीये किती नाही ओव्हर रेनफोर्स आहे otherwise if you will go by 8 mm what is the area of a single bar 8 mm huh 50.26 right बरोबर आहे ना
येस
हा
मॅम
so for that how many number of bars will be required 8 mm चे आपण 2 बार प्रोव्हाइड केले तर 100 येतोय ना आपल्याला 107 हवाय एरिया तीन बार लागतील so instead of that we are providing 2 bars of 10 mm fine
येस मॅम येस
okay fine now coming to the next step that is calculation of distribution of steel the minimum whatever is required accordingly the calculations are done I will skip these steps because it is already 3:15 and I want to explain you the diagram of detailing so these steps you can refer through the material whatever I am going to upload on VLP because this we have already explained or discussed yesterday the same things are done here okay simply applied the formula check for deflection we have calculated percentage of steel and compare it with assumed one it is coming safe but we have done it for separately for both the spans end span as well as intermediate span then check for shear same steps are there and we are getting a safe design for shear and check for development length again we have followed the formulas and we are getting the same same means safe value okay I want to explain this diagram now. This is the most important diagram. This figure I have taken from SP34, which is a handbook on concrete reinforcement and detailing. These are the guidelines and we have to compulsory follow these guidelines when we cast any construction, when we do the construction. Okay. This is a continuous slab. Now this is the end span. For that, we have already discussed that the bars are bent at a distance of zero point 0.1 L from the face of the support. From the center of the support, it is at 0.15 L. The bar is bent and extended in the compression zone, and a 90% bend is provided here as per the development length. Okay, this is for the end span or end support. What happens over a continuous support? This is very important. Now, over a continuous support, from this slab, suppose this is I'm calling as S1 slab and this is S2 slab. The bars, 50% bars are bent again at a distance of 0.1. No, for continuous support, the distance is 0.25 L1 from the center of the support. For end support, the distance is 0.15 L1 from center of the support, whereas for continuous support, the bending of the bar is done at a distance of 0.25 from the center of the support. So bar bending is done here, and that bent bar is taken up into the compression zone and it is extended up to this distance. What is this total distance? Now this total distance is, or it should be, 0.3 times L2 beyond the face of the support. Okay, the distance. Now the bar is bent and moved in the compression zone and it is extended in the second slab up to the length of 0.3 of the span of the second slab. Okay, this is important in case of continuous slab. Similarly, the bar which are coming from S2 slab, they are bent and extended into the S1 slab with the same criteria, with the same specification. So these details are very important and these details should be reflected in your sheets when you go for your term work. Okay, so this is very important diagram. As I'm uploading all these diagrams on VLP, you can study these in detail. This is the diagram for our design, whatever we have done or we are doing from yesterday. This is the S1 slab. We have already designed it. We have provided 8 mm diameter main steel. So these purple color lines are showing the main steel, and the description of the main steel should be written perpendicular to the bar. Okay, as per SP34 specifications. So 8 mm at 210 mm center to center. This is the description for main bar. This is main bar. The blue color line represents the distribution steel and its description is written perpendicular to the distribution steel. Okay, so it is 6 mm bar at 185 mm center to center. And the thickness of this entire slab is 100 mm overall depth. It is written in a box. Okay, so in this fashion, we have to give the details of all slabs. Now coming to this, these are the 3 continuous slabs which we designed today, we discussed. So the details of main reinforcement, 10 mm diameter at 200 mm center to center. Okay, that spacing we have calculated, and for the S2 and S4 slab, we have done the same calculation because both these slabs are subjected to same moment. Okay, so AST are coming same for both these slabs. Then this is 8 mm diameter. This is about the distribution steel. So blue color line represent distribution steel. Now here across the support, we have provided extra 10 mm bars, 2 numbers per meter. Extra means these are the bar which are bent and they are coming in over a support. This is a bar, bent bar from this slab. This is the bent bar coming from second slab. Okay, so other than this, the extra 10 mm 2 number of bars per meter we are providing here, that we have to write here because we cannot show it here. Okay, otherwise we need to show all the bars. That becomes very complicated. So simply we show 2 bars. One is bent to the left hand side, another bent to the right hand side, and what is the spacing between each bar, that we have mentioned here. Okay, similarly over the another support we have provided 10 mm 2 number of extra bars. So that we have written, and the thickness of each slab is written in the box here, which is 150 mm. Is it clear? In the examination also you are supposed to draw these diagrams. and in the sheet also you are supposed to show the detailing. This is called as reinforcement detailing, and the reinforcement detailing should be done according to SP34. Is it clear to everybody?
Then this is the plan now. Then how
Uh,
can we show that bent bars?
so it is, yeah, it is, we cannot see here, but every time it is not possible to show the cross section, na, it becomes complicated. That's why it is shown in the plan itself like this. Okay, these are the specifications given by SP34.
Okay.
So with this, we have completed the design of continuous slab also. The design of cantilever slab I am giving you as a self-study. The obviously the material related to this I'm going to upload on your VOLP course. You can refer it and do its understand the design of cantilever slab as a self-study. See, it is exactly similar to the design of simply supported slab, simply supported one-way slab. The steps are exactly same for cantilever slab also. Only we are providing the steel in the compression zone, not in the tension zone for cantilever slab. Because the moment the bending action is, if we consider the bending action in the cantilever slab, the tension is developed in the region above the neutral axis, not in the region below the neutral axis. Okay, so the main steel is provided in the top zone for cantilever slab. This is the only difference. The steps are exactly same, and I will give you the steps. You can study it easily. Okay. Now I have given you the link for attendance in the chat box. Everybody is supposed to give the attendance through the link given in chat box. Okay, so tomorrow's lecture we are going to start with design of two-way slabs. Any doubts in this?